So my name is Janine Burke-Wells. I'm the Executive Director at NEBRA, and I thank you very much for joining us today. Just a couple of housekeeping items. If you would please put your phones on mute during the call, except for our speaker. And those of you who are using desk phones, you can use *6 to mute and unmute your phone. I may try unmuting everyone at the end for questions and answers, but just to be sure, if you could use the chat function at the top to submit questions as they come up, I would appreciate that, and we'll try and save enough time at the end to get to all of your questions. So first and foremost, I would like to thank our sponsor for today's Lunch and Learn, Carbon Negativity. Robert Limmer is on the line, I am sure, but he would like for you to get to know BioForce right away, and so we'll get into the presentation. The presenter today is Valentino Villa, and Valentino is the co-founder and chief operating officer of BioForceTech Corporation. He was educated in Italy, and in 2008, he earned what's basically the equivalent of a PE in industrial engineering. Between 2008 and 2011, he co-founded 2 companies based in Milan, operating in the field of industrial automation and corporate branding or information technology services. And while working with these companies, Mr. Villa started the BioForceTech project with 4 other people, and in 2012 co-founded BioForceTech Corporation, which is in the U.S. He moved from Italy to Redwood City, California in 2013, started working as the CFO of Biotech, and in 2017, he transitioned to the role of Chief Operating Officer. As you will find out, Mr. Villa is an up-and-coming innovator. He's focused on eliminating waste products from manufacturing and transforming organic waste into sustainable products. So, of course, he came to be involved with Biosolids. His company, BioForceTech, is in the business of providing biosolid solutions using 2 efficient and high-value processes, the Biodryer and the P-Series Pyrolysis unit, which you will learn all about today. I just want to remind folks that just logged on to mute your phones, please. All right, so I know we're always looking for alternatives and new technologies for improving biosolids management, and especially dealing with PFAS and other contaminants of emerging concern. So pyrolysis is one of those technologies that we need to learn more about, and I hope you find today's webinar worthwhile. And without further ado, it's my pleasure to introduce Valentino Villa and pass him the presenter role. So let's see how this works here.
Thank you so much, Janine.
All right, hang on one second. I'm going to pass the role to you. Where'd you go? And hang on, Valentino. You can certainly speak here.
All right.
All right. I'm going to try and pass that off to you. And Valentino is joining us from the West Coast out in California. So it's early morning for him.
Yeah, not too early. I'm here since the AM, so it's all good. It's all you. Janine, can you see my screen now? Set up correctly?
No. You have not accepted the role yet.
You say that I...
All right.
All right, what about now?
It's coming. All right.
All right.
I can see your screen, and if everyone if you have an issue and it's too small, you can actually expand that to full screen on your computer. All right.
Background noises. I don't know if it's just your you too, Janine.
Okay.
Everybody.
And Valentino, you're coming in broken up, which is not good.
Yeah, I'm making a little trouble. I hear some background noise.
All right.
Everybody put the
Just if everyone could put your phones on mute.
Yeah.
We're sort of getting used to this fire engines in the background and dogs barking, but.
Yeah, it sounds better now, at least on my.
Okay, thank you.
Yeah, and you can see my screen, right? You confirm that.
Yes, I can. You're all set. Go ahead.
Thanks so much, of course, Janine, for the introduction and for having me today. It's a pleasure. Thank you, everybody, for joining today's webinar. I wanted to thank Robert Levert, of course, with Carbon Negativity for the support and for introducing us to this webinar, for the opportunity. Robert is one of our authorized representatives in the States. So for any question or for any follow-up question, please refer to Robert or to myself as well. Today, I would like to talk about our system that we developed in the course of the past few years. We love nature. As you can see, everything we do has to respect nature, and we really value all of the nature principles, and we apply that to the technology that we then developed. So starting from the bottom, from the heart of our company, our mission is to protect human nature and human health by providing technologies that deliver a zero-waste future, transforming organic waste into sustainable products. Our main goals are pretty much four. So, of course, to provide an affordable waste management system, to have and create a self-sustained and green process, to protect human health from harmful disposal practices, and every time we are to process organic waste, to produce a valuable byproduct from the organic stream. If we look at today's situation, of course, we're all familiar with what is happening, not just here in the US, but pretty much everywhere else in the world. I come from Italy, and the situation is exactly the same. Just in the US, about 100 million tons of organic waste are produced every year. And most of the times, what happens is that the waste is loaded into a truck and sent to landfills, to land application. There's still incinerations up and running. And in third world countries, sometimes we see still open fires happening. And you all know and you understand that all of these practices are not really sustainable from an environmental point of view. CO2, CH4 greenhouse gas emissions, and all of the other problems that can create for all of us. So we decided to change a little bit the mentality around the organic waste world and to present a new and innovative approach. So we developed and built solutions that can be installed directly at the source of the waste. So our main clients and are wastewater treatment plants. So the BioForceTech solution is meant to be installed directly inside the wastewater treatment plant in a modular approach or at collecting facilities. So for cities that collect, the yard waste, the food waste, we can process those streams in the same technology. And again, every time we are to process organic stream, our goal is to produce a valuable byproduct that can be reused for other beneficial uses. The solution that we developed is divided in two steps. The first step is called the Biodrying technology. The machine is called the BST Biodryer. It's a drying system that is needed for wet biomasses. Of course, Biosolids, it's our case right here, and the focus the most on today's webinar. And so the goal of the first step is to remove water from we are processing in a sustainable and sorry, here background noise. I remind to put the microphone on mute if possible. Thanks. And this second step is then a policy that completely transforms the nature of the renewable energy and a byproduct called Biochar. I'm going to tell you all about the Biochar in the next slide. The goals of this
Valentino, excuse me, it's Janine. Yeah,
yes.
Do you have like a headset on or something? Because you're definitely
I don't, and
coming
it's
in
not
broken up.
think because I'm talking straight to the computer and I'm just hearing background noises. I don't think they come from my end.
Okay. All right. I apologize for the interruption. Everyone else, please go back to mute.
Thank you, Janine. I was going to say that the benefits and the highlights of this solution, of course, it's a modular system that is meant to be installed, as I said before, directly at the source of the waste. We reduce the volume by 90%, which is a huge achievement in terms of truck transportation and the logistics and having to deal with 90% less material. We do not use any fossil fuel, so with the combination of the two processes, we achieve an energy neutral process from a thermal standpoint. We do not add anything to the biosolids in this case or to any of the other organic streams that we are processing. We just take them straight for the biosolids after the mechanical dewatering system. So, for example, centrifuge, belt filter press, screw press, whatever the wastewater treatment plant has in place, we can work with any of those. We don't need digestion, for example. We can work with the primary, secondary was. We can avoid digestion. And of course, the old system, we focus a lot on automation. Since my background and all of the other founders here, we have for automation, so we want to make sure to keep the operational and maintenance costs very low. And the concept, again, is to upcycle organic waste, biosolids in this case, into a valuable resource, which is the biochar in the end. Focusing on the first step, again, this is the BFT biodryer. I put some data here on the slide for all of you to see and to look at. I said that it's a modular approach. It means that we supply the biodryer in just one size. The machine is just one size. We don't really do custom engineering or building a bigger unit. We already maximize the dimensions and the performances of the unit to be delivered and shipped anywhere in the world in a regular container. And so each biodrying unit will be able to achieve the data that you see on the spreadsheet on the slide. As you can see, we have a throughput of about 1,200 wet tons a year if we have biosolids at 25% total solid. It's a batch process. The batch lasts between 48 to 68 hours, depending on the initial moisture content of the feedstock. We can load up to 8 wet tons per batch. The system operates at a temperature of an average of 150 degrees Fahrenheit, so we operate into the thermophilic phase. That is why we're able to produce Class A or exceptional quality biosolids, because of the EPA 503. Time and temp is definitely met, and all of the pathogens and all of the other requirements are usually met. Then, of course, it depends on the initial biosolids for the matter concentrations and other data. In terms of energy consumption, we're looking at less than 40 kilowatts hour per wet ton for the electrical consumption. And as a standalone technology, so if we don't have pyrolysis after, so with the energy recirculation back to the dryers, the thermal consumption of the biodrying system is less than 1.2 million BTU per wet ton. The system, as I said before, it's fully automated. We focus a lot on automation and to, of course, increase the performances of our technologies. And we guarantee a running time up to 8,500 hours per year. So virtually never stops. It's a very simple machine, and there's very few minutes to be done on the unit. This is a video that I think it will help you understand a little bit better how the technology works. It's an animated video. I hope you all can see it. So the first step of the process is called the growth phase. So you can see the vessel inside is completely empty. We don't have any moving parts inside. And so what we do at the beginning for the initial few hours is to inject air from the atmosphere with no additional energy being introduced. It's simply cold air that it's introduced into the system. And what it does, it's pretty much activate the bacteria that are already inside the biomass, the biosolids in this case, and bacteria will raise the temperature of the biomass by their natural breathing until we hit about 150 degrees Fahrenheit, which is our targeted temperature. And at that point, once we have a hot biomass, what we do is we augment the airflow within the vessel. So we push more air, still without any external energy source. And that way, we're able to remove the first 50 to 60% amount of water that is needed for us to achieve the right dryness afterwards, until we reach about 55% moisture content. And all of this is done just by the biological activity, so all of the bacteria generating heat. Once we reach that point, the moisture content, bacteria don't perform anymore as before because it's like composting. They need water content within the biomass to keep doing their metabolic activities. And so at that point, the energy, renewable energy produced from the pyrolysis step would be introduced to the biodryers to finalize the drying cycle with no natural gas consumption, but just renewable energy will come and finalize the drying cycle to achieve the targeted moisture content. And again, we can adjust the output in terms of dryness between 65 and 90%. Ideally for pyrolysis, if we have biosolids as a feedstock, we are targeting a solid content between 70 to 85%. So we don't need to go as dry as 90-95% if we have pyrolysis, but we can stop a little bit earlier. And of course, once the batch is done, we unload the vessel. We then feed the pyrolysis system in a continuous way, and the biodryer is loaded again with the new wet biosolids to start the new batch. These are some photos. Photos on the bottom are the first installation that we deploy in the United States, Silicon Valley Clean Water, here in Redwood City, San Francisco Bay Area. And the pictures on the top are two of the biodrying unit. As you can see, everything is skid mounted. So that is why the biodryer, pretty much we developed one size unit, because the unit comes already pre-built, assembled, and tested. So there's nothing to be done on site in terms of putting the unit together. Focusing on the second part of the process, so the second step, it's a pyrolysis technology. It's called the P series, because here for this step of the technology, we offer two sizes. We have a smaller unit, it's called the P5, and a larger unit that's called the P3 that has 3 times the throughput of the P5. So we have a bit of economy of scale for larger projects here with the pyrolysis step. And we partner with a German company called Pyrolysis. So we Pyrolysis developed this pyrolysis technology about over 10 years ago. And we partnered with them a few years back. And right now we are the exclusive distributors in the United States and other territories. And we pretty much do engineering together with them to make the machine and the units compliant for the US market. We make a few adjustments for automation and to make sure that we are compliant with US laws and regulations. Together, BioForceTech and Pyrolysis, we have about 25 installations worldwide. The oldest one, I believe, is 8 years ago. So we have plenty of references running on different feedstocks from, of course, biosolids to yard waste, food waste, and agricultural waste. For the one of you who are not familiar with pyrolysis, pyrolysis is a thermal decomposition of organic matter through the application of heat, but with no oxygen. So our pyrolysis system operates at a temperature between 800 to 1300 degrees Fahrenheit with no oxygen. Normally, from pyrolysis processes, you will obtain different byproducts. The innovative part of our system, pyrolysis, we did not invent pyrolysis. Pyrolysis has been known for a long, long time. But the way that we made it work and different than the other systems and permittable, of course, and usable for industrial applications it's because of the way that we manage the syngas. So what happens to the volatile matter once the biomass finds itself at a high temperature with no oxygen is that the volatile matter evaporates and turns into a gas. It's called a synthetic gas or syngas. And all of the old systems, at least until today, a few years back, they were all focusing on producing bio oil or other types of byproducts that they found to be having some value. Not for us. We don't see any value in those. And the way that we do pyrolysis is that we focus on high quality biochar production. That is all we're based on. And so the managing of the syngas is done differently. And I'm showing you right here. So you can see every unit will have a receiving tank on the top to accommodate about 2 tons of dry material. We have a special valve that allows the biosolids or the biomass to be introduced into the main reactor where no oxygen and a temperature set between 800 and 1300 degrees Fahrenheit is found. So the biomass will, in about 20 minutes, reach the end point, and that point will have turned into biochar. And the syngas, as soon as it's created from the volatile matter, we push that into a special combustion chamber that is called the flux burner. And so we do the oxidation of the syngas. So in a special way, it's a flameless combustion chamber. We have a constant temperature all the time with no visual flame. So we're able to keep NOx and all of the combustion pollutants to the very low level. And at the same way, we're able to first avoid the production of any type of other byproducts. So oil, vinegar, or tars, there's never going to be the case that we will have those byproducts because, again, for us, there's no value there, but problems. And at the same time, we will be able to generate a high BTU content, so high heating value exhaust gas, that it is reused within the main system, within the main pyrolysis reactor to keep the whole system hot and self-sustained. So once the pyrolysis system is fed with the biomass dry to the right point, then the whole system becomes energy self-sufficient from a thermal standpoint. And at the same time, we are able to capture the waste heat that is not used from the system because there's more that we produce, and exchange that for the production of hot water. Hot water is the form of energy that we produce from the pyrolysis system. Hot water at 200 degrees Fahrenheit that is used for the biodrying step. So that is the energy that we capture, that we produce, and that we feed back to the biodryers. The exhaust gas, before going to be discharged to the atmosphere, it goes through a double stage cleaning system with a caustic soda wet scrubber and an activated carbon filter to about sulfurs and heavy metals and possible other contaminants. And so the exhaust and the emissions for this type of technology are very clean and, of course, compliant with federal and local regulations. Talking about emissions and permitting process, it took us a while, being honest, to get the first permit because, again, we were the first probably crazy enough to bring this type of technologies to the market. And so something new, it takes always a long time to get our first permit for, and we are very proud of all of our achievements for the permitting process. Of course, the first step was to work with the EPA, and EPA gave us a approval for a non-incineration technology. So finally, we were categorized as a pyrolysis system because, of course, we don't do combustion of any solid. There's just the syngas, so it's a gaseous form that will get oxidated to produce the renewable energy and the biochar from the system. After that approval, we had to work with the local air district, which is, in this case, it was the Bay Area Air Quality Management District. That it's for us in the industry, it's very well known that it's very hard to get an air permit here in the San Francisco area because of very stringent regulations. And I am glad that we deployed the first system here because it's, how they say, you can make, if you make it in New York, you can make it anywhere, right? So it's like pretty much the same principle. We were able to get a air permit here in this very tough air district. And so right now, for all of the installations that we are deploying in the United States and overseas, the permitting process is much faster. We're looking at 6 months to 8 months because of all of the data that we collected, that we, of course, shown to the local authorities, and we're able now to expedite the permitting process because of all of the source testing and very stringent requirements that we had to go through because of, again, it was the first installation that we deployed to the United States market. Right now, we are working with CarRecycle. In California, there's a new Senate bill, SB 1383. By 2024 or 2025, 75% less organics. We need to pretty much go away from landfill. And so right now, we are working with them to get the technology approval as a landfill diversion system. Mass balance and pathogens and nutrients. If we take, for instance, 100 wet tons of biosolids before the two-step process, we have a reduction to about 25 tons of biosolids after the DFT biodryer. And in the end, we will have 10 tons of biochar. So we achieved a 90% volume reduction. Nutrients are normally preserved that are already within the biosolids. At the same time, from the pyrolytic step, because of the high temperature, because of the condition of the process, we have shown destruction of hormones, of pathogens, of course. And very important achievement, PFAS and PFOA, we have shown good results internally for now. So it's something that we're working on, and I would like to go to the next slide here. I know the PFAS and PFOA is a very hot topic. I've watched the documentary on Netflix and the movie that came out, and I've been documenting myself, and it's definitely something that it's present here, not just here in the U.S., but anywhere else in the world. Even overseas in Europe, they are, watching these compounds the same way. And so we decided in September 2019 to conduct internal analysis here. So we engaged with the lab in California, and we sent samples of wet biosolids. So after the mechanical dewatering of the wastewater treatment plant, of dried biosolids after the biodrying step, and of the resulting biochar. Of course, everything was coming from the same process. And so we have found, the lab found traces of 38, we analyzed 38 different PFAS and PFOA compounds. And of course, there were traces of those in the wet and dried biosolids. But as you can see from the table, amazingly, we have shown that the biochar doesn't have any of those. So it is a very big achievement for us and for our company. Of course, there will be further testing in the near future. But for now, we can be proudly saying that at least in the solids, we are showing something great. Destruction of those compounds that it seems very promising for us. Biochar. So this is all about the technology. The biochar is the core of our system, the product that we value the most, because again, it's an amazing product that has a lot of value, not in terms of just money, but for the environment first. We've been producing biochar for a long time, from the first prototype that we deployed to the full-scale systems that we have all over. And right now, the best use of biochar due to market conditions is used as a soil amendment, especially if it comes from biosolids, because of different reasons, but mainly for the nutrients that we're able to preserve within the end product. If you see on the bottom, we lose about 50% of the nitrogen, but we retain phosphorus and potassium up to 100%. Of course, it will be concentrated in the biochar. So that has been our main use and distribution of the product. At the same time, we're doing a lot of testing with private corporations, with universities, and so on, to explore other ways of using the biochar. Some of the most and amazing results that we have gotten so far are within the building material applications, and to offset additional CO2 by replacing carbon black. So those are the fields that we are working on right now, and we think within the next couple of years we will have very promising results for additional applications and uses of the biochar. Great example here that is happening in the Bay Area. Of course, we are located in Redwood City. It's a joint authority. They receive influence from 4 different cities. What is happening is that the BioForceTech system is processing the biosolids, and the city of Redwood City is reusing the biochar product. Instead of using fertilizer, they are using our product for their green areas and parks. So this is the best example of circular economy, and that is our goal, to keep everything and all of the resources in-house, possibly because, of course, we avoid truck transportation, and it's like producing a resource instead of having to deal with the waste. In terms of the carbon black replacement, we have done testing with USDA for bioplastics, and that is, again, one of our goal for the near future to come out with products for that replacement. Just to highlight again some of the advantages of our system. So once a client installs our system for the next 30 years, which is the lifespan of our equipment, the cost of managing biosolids or any other organic waste will be fixed and reduced. So there's no more tipping fees. Everything will be processed in-house. We're not impacted by the energy increase, labor increase. Everything will be fixed and reduced for the next 30 years. 90% volume reduction, which is huge. Truck transportation nowadays is producing a lot of greenhouse gas emissions and, of course, traffic and problems for the city. Energy positive system. So there's, of course, energy neutrality. Normally we find that with biosolids at 20% total solid in the beginning. And so it's a very big achievement to be independent from the natural gas consumption, because if you look at regular drying systems, they all consume a crazy amount of energy just to dry the biosolids. So with our system, we can achieve energy neutrality or can get to an energy positive system if we have enough dryness at the beginning with the wet biosolids. Again, the most important concept is to upcycle waste. So waste is not a waste anymore, but gets transformed into a resource for us, for the environment, and for all of the others that will come after us. We need to really take care of our planet right now. And the CO2 sequestration, of course, it comes indirectly from the production of biochar. Just to give you some reference, every 3 dry tons of biosolids processed throughout the system, we are sequestering 1 ton of CO2 from the atmosphere. So definitely it's something that can help all of us. First system in the United States, Silicon Valley Clean Water. I would like, of course, to thank them. They've been the best partner during our journey. Very innovative people. We wouldn't be here without them. So very, very glad to have found such partner in our early days. The system is being operational here for about 3 years. Capacity of about 500 wet tons a year for a 500 tons a year production of biochar. Couple of examples. Of course, we after the first installation in the United States, we are now deploying other systems here in the U.S. and overseas. And we found a great way of delivering projects is design and build. So this is just an example, but the message is that we're not just focusing on biosolids, although that is our main focus, but we start to see more and more interest from wastewater treatment plants or cities to process the other waste streams, organic, of course. And so we are focusing on a few projects that will have the inclusion of food waste and yard waste. We envision a project being a mix of the sewer sludge and food waste within the same facility to produce high quality and high density biochar, and a separate facility to process just the yard waste. Normally, yard waste doesn't really need a drying step before, but it's always good to have a backup dryer just to guarantee a constant product. So these are some of the projects that we're working on right now. The one on the left, it will be for the yard waste. So there's three P3s, pyrolysis systems, and one right will be the combination of the food waste and the biosolids. And I would like to say that this specific line doesn't have digestion. So it's an innovative approach to food waste and biosolids with no co-digestion. So it's very innovative too. And this is how everything will look like from an installation standpoint. So we respect nature, we make good products, and of course, they look nice too, at least in my opinion. So this is what we do. And that was the end of my presentation.
Oh, thank you so much, Valentino. It's generated a lot of questions, so thank you for leaving time for that. I'm going to leave everyone muted for a little while until I get through some of the questions that came through on the chat first. So the first series of questions were obviously from operators, and the last series were, in my opinion, from regulators. So here we go. What an operator was asking what the maximum feed water content is that can be processed. So the sludge content, what's the maximum water content that you can process with this technology?
So we always recommend to have at least 20% total solid. That is because of the energy balance. So normally, biosolids at 20% solid content, we're able to achieve energy neutrality from a thermal standpoint. If we have anything less in terms of solid content, the system will work with no problems, just maybe the need of additional natural gas because of the additional water to be removed. So just generally speaking, anything above 15, 16% solid content is welcome to the system. But again, 20% is normally where we hit the energy neutral spot.
Okay, thank you. And then another good question was, how is the sludge feed removed from the biodryer when it's done? I don't think you really showed that. That was an excellent question. Yep.
Let me actually reuse. Do I still have control of this screen, Janine?
Yes, you do.
Okay, let me go back to the biodrying system. So you can see here from these images. So the biodryer, again, it's a pre-assembled unit. So we always supply a shuttle screw conveyor on the top for the loading part. So do you see my mouse, Janine? Do you see me moving?
Yes.
Okay, beautiful.
Yes.
We have 5 gates on each biodrying unit. The unit rotates, right? So we have 4 wheels for which we allow rotation of the vessel every 4 to 6 hours, 2 RPM, so very slow, just to make sure that everything inside is uniformly dry. And so the gates are functioning as a loading system. So we rotate the dryer with the gates on the top position, receiving the wet sludge. Once the batch is done, so we have a dried biosolids at that point, the vessel will simply rotate, bringing the gates to the bottom position. And you can see here from this picture, we have a chain conveyor that will receive the dried biosolids from the same gates. So we load using 5 gates, we unload using 1 single gate.
Wow. All right. Yes, no, thank you for showing that. So another question was whether any of the components of municipal sludge or waste that could foul that flux burner. They were thinking specifically of siloxanes or something like that.
We haven't found any problem, honestly. In over 80 years of installations and operations, we have processed a lot of different biosolids from different sites all over the world and different other feedstocks. And flux burning is amazing. The operating temperature is above 2,000 degrees Fahrenheit for the combustion and oxidation of syngas. So it's been running terrifically for us, and we haven't found any problem for other compounds within the municipal sludge.
Okay, excellent. There was another question about how or whether you were capturing any energy from the combustion of the syngas. I don't know if you could go back to that that?
Yeah, let me go back to the slide about the schematic here. So it's pretty straightforward. So this is the main process reactor, right? Where, again, we have a temperature set between 800 and 1300 degrees Fahrenheit with no oxygen. So the syngas naturally creates from the volatile matter. And what we do is that we have a slight vacuum system that pushes the syngas, the combustion chamber, the flux burner. And so simply by combusting the syngas, it's like doing a combustion of, methane. You have exhaust gas. You have high heating content exhaust gas that we capture and we recirculate back to the outside part of the reactor without having it to touch the material. And in that way, the process becomes self-sustaining. We use about 1/3 of the energy that is being produced here by the combustion of the syngas. The remaining 2/3 are exchanged and transformed into hot water at 200 degrees Fahrenheit. The hot water is then fed back to the biodryers. You can see here, this is a second heat exchanger that gets and receives the hot water from the pyrolysis step and transports that into hot air. So that is how we capture the hot water and finalize the drying part.
All right, excellent. I have a series of questions here, Valentino, about what kind of contaminants are in the gas and the recycled water. Similar types of questions. Are you testing the gas or any of the return streams for PFAS? And again, what about air emissions? Have you tested any of anything that's going into the air for PFAS?
Yes. So the syngas composition, it is nothing that we have detection on. We've done testing in the past, but from the way that we manage the syngas is that since we completely combust it and oxidate it, right? What we monitor and what we had to monitor were the stack emissions, right? So whatever is left after the combustion of the syngas, after the exchange for the hot water production, after the wet scrubber, and after the AC filter. So we've done intensive source testing here because of the requirements from the San Francisco Bay Area Air District. And so we were able to get a permit that was very stringent. There was no really a category for pyrolysis, so we've been given very, very low emission allowances. And so everything that we are emitting is pretty much CO2 and water. There's some other compounds. We have not analyzed the stack for PFAS and PFOA yet. Again, that was something that we did internally in September 2019 for the solids part. Further testing will be done here from our company. We're still evaluating how and when, but right now what we can show is about the solids, PFAS and PFOA destruction. So we have not analyzed the condensate water from the wet scrubber, nor the stack emissions for PFAS and PFOA yet. The theory behind it, it's pretty simple, at least for the solids destruction point. PFAS and PFOA, normally the highest boiling point is around 250, 260 degrees Celsius. The main pyrolysis reactor operates between 450 to 650 degrees Celsius. So definitely the boiling point is heat. And so all of those compounds will end up in the gas, the syngas. The syngas, we combust that over 2000 degrees Fahrenheit. So for what we've seen in earlier studies, they've shown that over 2000 degrees Fahrenheit, that high temperature is able to break those compounds apart. So theoretically, what we will expect from further testing at the stack is still known detection levels of PFAS and PFOA. And we also have an activated carbon filter, which, for what we know, we've seen that activated carbons can be another alternative to capture those compounds. So further testing will be carried on internally. For now, what we have seen is just on the solid side.
Okay. No, thank you very much. That's great that you're going to be doing that testing of the syngas, the return water stream. And also, there was also a question about the granulated activated carbon filters. That's part of the system. So, yeah, we'll be interested to see what you get for results for that. As you know, this area of the country is the epicenter of PFAS issues. So
Yeah.
there was another question, Valentino, about the actual uses of the biochar material. There were some questions about what it contained for nutrients, and the person asking was assuming that you were referring to phosphorus, calcium, and that stuff, but not nitrogen. Can you speak to that biochar product a little bit and where it's actually being used?
Yeah, absolutely. So biochar, again, it's pretty much carbon that we are able to capture in a fixed way within the biochar products. The composition of the biochar, it depends on the initial feedstock, right? So if we were to process biosolids, the composition of the biochar would be very different than processing wood waste, of course. Roughly, the carbon content of biochar from biosolids will be between 28 to 35%. Nitrogen, phosphorus, and potassium still remains pretty high. So that is why there's a lot of value, because it's not a fertilizer, but it's a soil amendment. So biochar, what it does to the soil, because of the porosity structure. So biochar is very high in porosity, right? So once you apply the product to the soil, what it does is that it helps with water retention. So by applying biochar, studies have shown that you're able to save about 3 times the water that you would have needed if biochar was not being applied. And same with nutrients. Because of the porosity structure, the biochar is able to hold water and nutrients for plants to be slowly absorbed. CO2 sequestration, pretty much we're putting fixed carbon back to the soil and will stay there for, there's no specific time, there's never been studied for how long the fixed carbon will last, but it will be hundreds of years probably, because it gets eaten out. And so that is the value of the biochar. It is a safe product. We got the CDFA approval from the California Department of Food and Agriculture. It's considered exceptional quality biosolids by EPA 503, so there's no really that many problems in distributing the products. And it's great. It's just we have partners in the agricultural business. We have farmers that have been using our biochar for quite a bit right now. And I mean, the city is using the biochar to apply that to their parks and recs. So it is not biosolids anymore in our vision. It still is under EPA 503. I understand that. But the product is such a beautiful product with such tremendous properties that as BioForceTech Corporation, knowing the value of the product we are producing and supplying, we are willing to take responsibility and ownership of every pound of biochar that is produced throughout our systems, find a market, and share profits with the client. So a client is producing biochar. It's not, they can just leave it to us. We find a market. We know it's a great product. We have a great network of distributors, of people who trust this product, that we will find the best use for it. And right now it's being to be found as an agricultural product. But again, the goal of our company is to further and increase the use and the applications for this product for something even more beneficial. So to increase the CO2 sequestration, if we were to replace carbon black, instead of having a 3-to-1 dry tons to CO2 sequester, we will have 3 to 4.5 tons of CO2 sequestered. And that is all what we want to do. I mean, the goal, the mission of our company is truly to preserve nature and to bring sustainable solutions to this market, because we really need it. The way that we manage waste has been pretty much the same since 30 years ago, and definitely there's the need of a change. New contaminants, new things coming every year, and we are, not doing good things to the planet. So it's about time to make a change, in our opinion. And biochar is truly an amazing product. And you can Google it. You can Google biochar on Google, and there's like 10,000 articles every year coming out for the benefits of the product. So we truly believe as a company that biochar, it is the future of organic waste and will bring a lot of benefits to all of us.
All right. Thank you for that answer. Couple more questions from operators, it looks like to me. One was, how are you controlling emissions from the biodryer if it's not associated with the pyrolysis unit?
Very good question. So the pyrolysis system already has cleaning system built in within the unit, so there's no need to add anything to the pyrolysis step. Everything is pre-built and is designed as is. The biodryer, we can work with different solutions. So what we have here in Redwood City, for example, we have a biofilter, so wood chips, coconut fibers, other organic matter. So you all have all understood that we love nature. So we like biofilters, but any double stage scrubber, water scrubber with a further carbon filter, that will do the job. The main compounds are VOC and ammonia, as any regular dryer. There's nothing more, there's nothing less. It's standard emissions from any other dryer. So biofilter will do the job. If there's space concern and constraint, then we can go with a more compact solution with maybe a double stage scrubber. But regular technologies will do the job.
All right. Another question from, I'm sure, one of our operators. What's the source of the scrubbing water? And what's happening to it after that? Is it going recycled back to the treatment facility?
Yes.
So how much is being used?
Yes.
Talk about that scrubbing system.
Yeah, it's very, very low usage of the scrubbing water for the pyrolysis system. I have to double check with my engineering team. I believe we're in the order of probably 20 gallons a minute or something. I have to check with my engineering team, but we have data. We have to show those. We're doing a further context here. For the biodryers, the condensate water, it's about 1/3 of the water removed. It's normally sent back to the headworks of the plant, the treatment plant.
Okay.
In terms of the percentage out of the inflow, we're looking at about 0.0009%. So yes, there is ammonia in the condensate water, but the dilution is such a high number that the treatment plant doesn't see any variation based on their current permit for the ammonia load. And the remaining 2/3 normally go through the cleaning system. So either the biofilter or the scrubber or whatever other cleaning system we will have installed. And that is the diversification of the condensate water for the biodryers. For the pyrolysis wet scrubber, it's very minimal. And I've been working with different engineering firms, and they've been asking me this data, and I was able, of course, to give the data, but it was no concern for nobody in terms of it's very minimal amount.
Okay, thank you. And another operational question regarding the feed, the sludge feeding into the biodryer. Does it make a difference if it's digested sludge or not?
No, not really. So undigested sludge will have a higher BTU content per dry pound, so a higher calorific value. That means, and the volatile will be higher, of course. So that means that there will be some more feed for the bacteria. So the biodrying process will be a little bit faster. And at the same time, the pyrolysis step will be able to produce more energy with the less dry feedstock. So we have installations running on undigested sludge, and there's been no problem. The technology works exactly the same. The throughput data will be slightly different because of the higher BTU content per dry pound, but we're looking maybe at a 5 to 7% difference. But the technology and the way that we process is exactly the same, and results are exactly the same.
All right. Thank you very much for that. I'm tempted to open the line here for other questions, although Robert has been helping answer some of the questions in the chat box. And I would, as a follow-up, if there's any other questions that we didn't get to here, when I send out the materials after the fact, maybe we can get those answers out as well. Let me go ahead and take back control here. And we'll see, we'll open it up and see if there's any other questions here. But this was a very interesting. Share the screen. All right, so thank you everyone who's attended today. If there are any other questions, I'll leave the screen open for a little while. You can add them in the chat or feel free to email us. We will check with Valentino, get answers, and get them back out to you. And this was a very interesting discussion today, I think, and I appreciate Valentino's expertise and wanting to share all the information that he has, and specifically Rob over there at Carbon Negativity. Thank you very much for sponsoring this session and for helping us to answer some of those questions. And with that, I just wish everyone a very happy Memorial Day weekend. Thanks again, Valentino and Rob from NEBRA. Goodbye, everyone.